Hey everybody, I just wanted to let you know what's happening. So I've been running these live streams every day, and for some odd reason it seems like the pen that I've been using to draw on the computer has run out of battery. So let's put this here. So I'm actually right now trying to get that right back working so that we can go again. Of course there's always a plan B. The plan B is that I'll write a little bit less clearly. But hang on a minute, we'll be right back. Hang on a minute. Hello, everyone. Thank you, everyone, for putting up with that. I will say that in this new world of the using digital and internet to reach everyone, there will always be some snags. But I will tell you what actually happened. It appears that because I've been using this computer to give so many of these live streams, for some reason the touch screen stopped working. So what just happened in the last 8 minutes is problem solving. Actually, whenever you have anything that breaks or crashes, it doesn't mean it's over. And in fact, that's also true if you're ever doing a math problem or trying to do a math test. If plan A doesn't work, you try plan B. So I'll tell you what is usually happening, in case you're actually curious how this live stream is even done. Usually I use a computer for which I can draw on the screen, and then you're able to see what I draw. However, in this case, for some reason the screen actually stopped responding for me drawing on it. So I actually switched to another device, this thing here, which lets me draw on another pad. And then when I draw on the pad, I can see it on the screen. So in general, whenever you do something, if the first thing doesn't work, just try the second thing. And we'll see if we can use this to run today's session. With that, let me switch to my Blackboard, which I think now works. I tested it by writing hi. Actually, strictly speaking, I probably shouldn't have written hi. The correct thing that you write whenever you test something is you should write something like, let's try, does this actually work? Yeah. Hello, world. That's often how you test whether or not something works when you're doing digital things. So, hello, world. I think we may have some part of the world on this particular live stream. Happy to be with you again today. Just to set out the way that, oh, you can't see it? Is that true? Double check. People see this? Are people good? Do you see this hello world? If you see hello world, please let me know. Hello world too. Okay, very good. I think we see it. Glad it's working. Right. So also I should maybe say the way that we're going to run this stream. We always will invite people to post the questions that they might be interested in. And this is an Ask Math Anything. AMA often stands for Ask Me Anything, but these will be about math. Ask Math Anything. And when I say anything, what I mean is I have not prepared in advance to answer any of these questions. But that's actually the fun part for me. I like to have a challenge every day, and the challenge is, can I come up with a mini lesson, improvised, for anything that you might ask? So that I know what age group or what level to target, could you please type into the chat what math you're taking right now? I'm looking at the chat. Whenever I look in this direction, that lets me see what you guys are all typing. What kind of math class are you guys taking right now? I see something's coming already. Algebra, Geometry. Somebody's Common Core 6. So I'm actually seeing 5th grade, 6th grade. I see a lot of young people here, and I think that's great. I do want to say, I know that we have some loyal watchers of this daily live stream who maybe were interested in high school math or even later. I want to tell you, if you're interested in those topics, I recommend you come to the live stream that's on the weekends. On Saturday night at 8 o'clock p.m. Eastern Time here in the United States is when we run that one, which is a little bit maybe more challenging. But for this particular live stream, I want to try to aim on something that could be helpful to as many people as possible. Because, you know, we do live in this world where everyone does benefit from knowing how to think about math. So let's now look at some of these questions that people might have asked. And I will also say, I'm going to try a new tactic today, which is that if I see a question and I see an angle I can spin it in that might be interesting to even people in 8th grade or middle school, I will try to do so. So, let's see. I see that somebody has asked a question about Simon's favorite factoring trick. This is an interesting question. Let me write this thing down. So Simon's favorite factoring trick. It'll take me a moment to get used to this new way that I'm writing on this board, but I think this should be okay. So we want to talk about, Simon's favorite factoring trick. You'll see that the handwriting is not the same as usual. It's because right now the board I'm writing on is not the same as the screen. So I'm now learning how to write somewhere and also look somewhere else at the same time. But we'll get better as we go. That's how we learn anything. This Simon's favorite factoring trick is related to trying to solve questions where you might be interested in finding whole number solutions to a problem. Let's see. Suppose I'm asking, are there any whole number solutions to an equation like this? Oftentimes it's going to have an x and a y. And you're kind of curious, could I ever get any solutions where x and y are both integers, whole numbers, but somehow xy you often write something like this: xy minus 2x plus, let's say, 3y equals, let's put a random number here. There might not be any solutions, by the way. We'll find out. Are there any whole number solutions to this, where I need x and y both to be whole numbers? Some people say yes, some people say no, but how would you know? You see, you have both x and y here. So when you look at an equation like this, you can't really just say solve for x. If you tried to solve for x, you'd still have some y's lying around. So this Simon's favorite factoring trick is something where you use a technique that people learn in Algebra 1 called factoring by grouping. I don't know if that's how it's called in your textbook, but that's how it was called in my textbook when I learned this in Wisconsin. So when you factor by grouping, what do you actually do? Does anyone want to help me out? If I have an xy minus 2x, you might be like, what do you mean? What kind of groups? Well, you can factor out something with the xy minus 2x in the sense that this part, the xy minus 2x, there is a common factor on both of those terms. Does anyone know what you can factor out of both xy and 2x? You can factor something out of both. Take x out. Let's try it. So what happens if I take x out? I could say that that part is x times y minus 2. Okay, all I'll say there is, I guess that's kind of cute, but it's not clear whether this is useful. Let's see what we could do next. Well, let's leave the plus 3y here. And in algebra, we just need to leave the left and the right hand sides, let's say, treated the same way. A lot of people will think that learning algebra is complicated. In my opinion, algebra has one key concept that once you understand, a lot of algebra becomes easier. And that is, whatever you do to one side, you have to do to the other side. And after a while, if you have beaten up the sides enough so that one of the sides is nice, then you're done. But right now we're not done. It's not that nice yet. However, I see some people are saying minus 6 from both sides. Let's try that. What happens if I decide to do the same thing to both sides, which is subtracting 6? Some people will ask, why in the world will you subtract 6? Well, let's find out. If I subtract 6 from both sides, remember, I have to do the same thing to both sides, so this is legit. Then so far, this is still the same set of solutions as that one, meaning that this equation, if I find out what x and y satisfy this, is the same as up there. Okay. In that case, why is this so exciting? It's because this 3y minus 6 you can also factor. Does anyone know why this is exciting? That one, you can also factor something out of both terms. Yeah, you can factor 3 out. Thank you very much. Harry Potter. Wow, I have a wizard here. Okay, so Harry Potter says factor the 3 out. If you factor the 3 out, this part becomes 3 times y minus 2. Okay, let's keep the x times y minus 2. I apologize that they're not perfectly lined up. I am actually learning right now how to use this backup tablet. And I'm doing this, and I'm even telling you I'm doing this just to show you that, this is not just about learning math. In some sense, this live stream is also about learning what to do if anything is not what you expected. Okay, so the right side, 10 minus 6 is how much? Help me out. 10 minus 6 is, I'm looking at the comments, 101 is prime. That is true, but what is 10 minus 6? 4. I see it. So 10 minus 6 is 4. So far, I still have the same equation. But now here's where the factoring by grouping comes in. And factoring by grouping is something that is usually taught somewhere in an algebra class, sometimes even in Algebra 1. What can I do here? Why is it so good that both of them have y minus 2? Because I can now factor again. The left-hand side is something times y minus 2 plus something else times y minus 2. So what can I put? I see it. Ivy He says I can put x plus 3 times y minus 2. Okay. So now the left-hand side, I can say I have x plus 3 times y minus 2 equals 4. Oh, I got lucky. It looks like there will be solutions. I was asking, are there any whole number solutions, integer solutions for x and y? But once you write it this way, there are. What does that mean? So you see, if x is an integer, so is x plus 3. And vice versa. If x plus 3 is an integer, so is x. If y minus 2 is an integer, so is y. And if y is an integer, so is y minus 2. So this question is actually asking me, how can I find some integer times some integer equals to 4? Can you tell me all the ways to make integer times integer equals to 4? Go ahead and write it into the chat while I just go and copy this x plus 3y minus 2 equals 4 on the next screen. X plus 3, y minus 2 equals 4. Okay. I see already people are saying there are ways to do this. You could, for example, have that the numbers multiplying to 4, it could be like 1 times 4. That would be possible. What would that mean? So let's write down a couple of ways that you could make things multiply to get 4. Maybe I'll write it on the right side. I could have 1 times 4. That times is a times sign, not an x, equals 4. Okay. At this point, what can I do for this 1 times 4 equals to 4? What does that mean about this x plus 3 y minus 2? I could say that one way to make this be 1 times 4 would be to say that x plus 3 is 1 and y minus 2 is 4. Can anyone tell me what choices of x and y that would correspond to? Well, I could get the x plus 3 equals to 1 if x was equal to how much? Oh, you know what? I have an idea. Let me use green, because I'm going to have a bunch of rows, and maybe I'll just make each row a different color. So, if I use this, oh, that's interesting. Something else happened that's not good. It looks like the drawing tab froze. Oh no. So we have different kind of thing now. I'll tell you what. So what we'll do, it seems like the computer is acting up, but what we can always do is we can always restart the drawing. So we'll do x plus 3, y minus 2 equals to 4. Okay. Let's get rid of the drawing app and close it and open it again. Take it out. Here we go. Okay. I think actually what's going on is because I'm using this tablet and resting it on the keyboard, I'm probably accidentally pressing some keys that I shouldn't be. So we had x plus 3, y minus 2 equals to 4. And we had over here, we had the 1 times 4 equals to 4, and that gave some time for everyone to think. So what you see is that you could, for example, get x plus 3 equals to 1 if x equals negative 2. Is that what people are saying? Very good. X equals negative 2. And you could get y minus 2 to be 4 by making y equal to 6. So that appears that it is one of the solutions. Is that actually one of the solutions to the original equation? What in the world was the original equation? Let's try to remember what that was. I already forgot. Does anyone remember? This was xy minus 2x, I think it was plus 3y equals to 10. That was the original equation. Does this actually work? Can you guys test? Minus 2 times 6 is minus 12. So that would be minus 12 here. Let's just double check the green equation, the green numbers, see if it works. This would be minus 12. And then the minus 2x would be a plus 4. Okay, plus 4. And then there would be a plus 3y, which would be plus 18. What is that? Oh, minus 12 plus 4, that's negative 8. Hey, it works! Okay. So I have found one of the solutions to this equation. I could have x equals minus 2, y equals 6. But now you see how this works. The way, yes, we want whole numbers as solutions. You want me to turn my sound up? One moment, please. We can do that. Oh, wait. Actually, our sound should already be up. Let me do another quick check. So somebody thinks that the sound is low. Does anyone else think that the sound is lower than usual? Because actually the settings are exactly the same as what we used last time. So do people think, so let's say this. If you think the sound is the same as what it was last time, please say yes. Let's see what we've got here. Chat disconnected. That's interesting. Okay, people seem to think, some people think yes, some people think no, so here's what I'm going to do. I am going to just turn it up a notch. We'll just do that right here. So, we just turned the sound up a notch. Let's see if this works. Okay, let's continue on. And if this is just going to turn up a notch, I hope it doesn't blow your eardrums out, but we'll go on as it is, okay? So let's keep going. The other ways to get something times something equals to 4. What else could I do? I saw that some people had said, oh, some people saying so loud. Ah, okay. Well, let's keep going. Somebody made a comment about the quality. I will say that whenever we do anything online, especially during this period when there's the coronavirus, when a lot of things are not working, indeed, we often have to figure out how to problem solve to make things work. And so, in some sense, we're living right now during one of the very unusual times in human civilization. And I thank all of you for working with me to try to make this thing work out. Let's keep going. If I want to find other ways to multiply to 4, we could also do 2 times 2. I saw some people say that. So you could do 2 times 2 is 4. And if we do 2 times 2 equals 4, what x and y correspond to that? I think I saw someone already put in the chat. If I want to make x plus 3 equals 2, I could do it with x equals minus 1. If I want to make y minus 2 equals to 2, I could also do that with y equals 4. Does this actually work? Let's quickly check. I mean, they should actually all work because the equations were equivalent. But if I take x times y, I get negative 4, right? Negative 4. And then minus 2x is a plus 2. And then plus 3y is plus 12. Yeah, that's good. That's 10. So it works. And now, what else could I have? Other ways to multiply to make 4. I could make 4 with 4 times 1. Okay? So 4 times 1. We'll do a 4 times 1 equals 4. And so what could I do? If I want x to be 4, I could use x equals 3. No, I can't. That's a mistake. It's x plus 3 equals to 4. So it's x equals to 1. Okay? And if I want to make y minus 2 equals to 1, then I use y equals 3. And you can double check. This actually does work too. But is that it? Am I all done? Are these the only 3 ways to choose integers for x and y to make the equation work? You have to remember the negatives. So actually, this is one of these complicated, not complicated, it's a trick question that it's unfortunate that sometimes people forget to use the fact that negative times negative is positive. So there are also some other solutions. Let's use green again. You can also do negative 1 times negative 4 equals to 4. If I want to make negative 1, what would I use for x? Help me out here. X plus 3 equals negative 1. So x should be negative 4. Okay, good. And y minus 2 should be negative 4. So what should I use there? I should use negative 2. And if I took negative 4 plus 3, I'd get negative 1. If I take negative 2 minus 2, I get negative 4. So I get this. Okay, so we are good with this. Let's see, what else can I do? I have other negatives also. I can also do negative 2 times negative 2 equals to 4. Let's try to get the alignment back. So here, if I want x plus 3 is negative 2, I guess that's x equals negative 5. And if I want y minus 2 is negative 2, I guess that's y equals 0. Okay, I'm just kind of doing all of these calculations quickly now because the calculation is not the interesting part. The next thing is the last one, which is if I want to have negative 4 times negative 1, if I want that to be 4, then this would come from x equals negative 7 and y equals 1. Okay, is that all? Do I have anything else? Well, this should be everything, because these are all of the different ways that you could factorize 4, whether using positive numbers or negative numbers. You can't make a 4 by taking a positive number times a negative number. So that's it. So this is sometimes, I think this is what people on the internet call Simon's favorite factoring trick. That was what some people had brought up. So Simon's favorite factoring trick I had seen, actually the first time I saw it was when I was way after I ever did math competitions. So I was like, I didn't know it was called Simon's favorite factoring trick. I thought it was just called factoring by grouping. But by the way, the first time I ever saw this, I thought it was really clever. Because otherwise, how do you do a problem like finding all of the integer solutions to that? Like guess and check? That's what I did before. But the first time I saw this was when I was doing math counts. And I saw in one of the solutions of a problem I could not do that the person had done this. And I said, that's brilliant. And so, this is clearly Professor Simon's favorite factoring trick. Apparently he thought the same thing. Who's Simon? You may wonder who Simon is. Is Simon somebody who was like, around when Pythagoras was? Maybe Simon came up with this a long time ago. If anyone's curious, Simon is actually a guy who lives in the San Francisco Bay Area right now. He's actually even younger than I am, I think. but he happens to help coach a lot of students to learn very, very advanced abstract mathematics, which is actually way beyond competitions. Very, very interesting guy. He got a PhD in mathematics, and then later on, he decided that he wanted to teach people what kind of math you learn in graduate school instead of learning about competition math. I love talking to him whenever I go by the Bay Area, but I'll say this is actually a real person, this Simon. Fun guy. Okay, next question. Let's see. Yeah, Simon is a very interesting person, very interesting person. So let's see, what other questions can we take? And I see that some questions have already come in, and we very fortunately, our moderation team has helped me to try to identify the questions that might be the closest level to this audience. And we want to choose questions which people who are in middle school could understand, and maybe people who are in high school would even find interesting. And the next question that I see is how to find the least common multiple of the first 10 integers. But what I'll say is, actually that question is an exact question in our daily challenge course. So unfortunately, since there's a bunch of people here who may have taken our daily challenge course, I don't quite want to do that question again. Although I will say that the question in our daily challenge class is not exactly that. Our version is more interesting. It's more interesting to ask that question where you don't include 7. But in any case, because that question already has appeared before in some of the things that I do, we'll skip that one for now. And if you're curious, maybe check out the course and you'll see. Other questions here. How many digits of pi can you recite? I'll hit that one right now while our moderation team is finding some questions to use. 3.1415926. That's it. Because that's all I needed to make my phone number. My phone number is actually, as some people know from the weekend live stream, my phone number is 844 and then 314159223. 3 because you have to round up the 6. And at this point, I'm going to turn my phone maybe onto silent because I had forgotten to do that earlier. But now we're good. Okay. Yes, that's all I know. Just enough digits of pi to make a phone number. What else can we have? Oh, I like this. Zeno's paradox. Let's hit Zeno's paradox. Again, because that's something that we can use that hits a lot of ages. So Zeno's paradox. Let's write this down. Oh, I want to make sure that my handwriting is clear enough, because otherwise you might think of it as saying the zero paradox. But it's Zeno's paradox. Okay, what's Zeno's paradox? Zeno's paradox says you have a guy, I guess the guy is called Zeno. So you have a guy over here called Zeno. And Zeno's paradox is that Zeno is confused. Okay, I'm done. Are you satisfied? No. I'll tell you more. Okay, so this is a story, right? So you got Zeno. And Zeno looks at, a wall. Oh, hello. Somebody from Minnesota has just called me. Hello. Okay, so Zeno, let's pretend Zeno is trying to walk to, well, I guess Zeno was, I think, probably Greek. So maybe they didn't have that many walls, but they probably had rocks. Here is a pile of rocks. Zeno is walking towards a pile of rocks. Rocks are easy to draw because they're just circles. Okay, and what Zeno says is that it's going to take forever to get to that pile of rocks. Because, for example, first, Zeno has to get halfway. See all of this distance? First, Zeno has to get halfway. And then after Zeno gets halfway, then Zeno has to get halfway further. Right? From there, he has to go another halfway. And then after he does that halfway, Zeno has to do another half of the way. By the way, if we wanted to give some labels to this, what we would say is that first, Zeno has to walk a distance of halfway to the rocks. Then Zeno has to walk a distance of a quarter of the way to the rocks. And then Zeno has to walk a distance of 1/8 to the rocks. And if you just have to keep going, look, Zeno has to go with infinitely many little segments. So the Greeks were concerned, or at least Zeno was concerned, I shouldn't say all the Greeks, Zeno was concerned, in order to get to the rocks, he needs to do infinitely many things. He needs to go halfway, then he needs to go a quarter of the way, then he needs to go 1/8 of the way, then he needs to go a 16th of the way, and we'll never get there. It's infinity. Jason Chang says Zeno is crazy. Maybe. Actually, I think what was going on, though, is that Zeno was basically asking the question, if you add up infinitely many numbers, is the answer always infinity? And if you haven't really developed a good understanding of numbers yet, you might think, if I just add up infinitely much stuff, where every single time I'm adding some more, I'm really adding some more. It's not like adding zero, you know. Over here, it's like, there's still a little bit. If you just keep adding a little bit and a little bit and a little bit, surely it will go to infinity. I mean, if you've never thought about this before, it does seem reasonable that you just keep picking up more stuff. But ultimately in math, it turns out that when you add up all of this stuff, you don't actually get infinity. In fact, it converges to 1. And now I'll use that to say a little bit about how we could even prove that. Okay? Because I think we can have, yes, someone says it's a geometric system, a geometric series, anti-Tiases, but I want to talk about this in a level of depth that you might not be as used to looking at. Okay? So I want to talk about 1/2 plus 1/4 plus 1/8 and so on. 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. What is this? Well, actually, I know what the answer is. The answer is because we all know in real life that Zeno would get to the rocks and trip and fall over. So it's possible, right? He would get to the rocks eventually. And he would get to the rocks in a distance of 1, right? So we know the answer is 1. But now I'm curious. How do people usually explain why this is 1? I'm very curious what people usually say, because here's where we get to dive in to talk a little bit about how math works. Why is this 1? And I'm going to take a sip of water while I let some people post some things into the chat. What's the first thing that you do whenever you're doing this kind of problem? Somebody thinks that Zeno will never get to the rocks. So let's see. Usually, yes, I see that some people are saying it's glitching. I'll tell you why. It's because this time I'm trying the very low latency model on YouTube. So actually what this means is next time we won't. But with YouTube Live, you actually can choose a bunch of different latencies. Latency means how many seconds after I say a word do you hear it. And we were previously using the setting called low latency. And what that meant is if I said something and asked you a question, it would actually take about 5 to 10 seconds for you to even hear me ask the question, and then you'd type something into the chat. So that was slowing down the rate that people were answering questions. So this time I decided to switch to ultra low latency to see how it worked. And of course the warning was sometimes it will have trouble with the buffering. But other times, what it will do is it will let it be so that when I ask a question, you guys get the question in fewer seconds. Okay, so let's see. What do we have here now? Yes, so let's see. So we have a geometric progression. People are saying a over 1 minus r. And indeed, a over 1 minus r is the formula. But I'm curious why the formula is true. A lot of people will say, what does this equal? How would I prove it's a equal a over 1 minus r? Some of geometric progression, I agree. But I'm asking, like, why does that work? I actually want to ask the why. It's usually because what happens here is that people say, okay, some people are saying no idea. I'll show 2 ways of doing this, okay? The first way is I'll say some people say, I don't know what the answer is. So let's call the answer x. X is now the answer. And so let's draw a better x. Okay? X is the answer. Now, if x is the answer, what are we able to do? Some people would say, well, if x is the answer, then if I have 1/2 plus 1/4 plus 1/16 and so on, you could take this particular equation and do what with the equation? I'm actually curious what people are usually learning in the textbooks. And you know what? Because I see so many people saying the word glitch, I am going to, somebody said multiply x. That's pretty good. We're getting there. But what I'm going to do here, because people said glitch, there is something I am able to do inside this live dashboard. And what I'm going to do is I'm going to see if I can just switch it to the regular latency right now. I'm not sure I'm able to do that midstream. But if I am able to do that midstream, then what that will do for all of you is at least it will bring it back to the latency that we had before. So I'm just going to do that here. We have this, go to live dashboard. One moment. While the chat, you can still use the chat to put in your comments about what you multiply by. People said multiply x. So we're here, stream options, and I've now learned a lesson. Oh, that's interesting. Actually, it was on low latency the whole time. And also it says we can't change it. Okay, no problem. I'm just going to go back and we'll continue. Okay, in that case, what I'm going to tell you is the fact that it's glitching in that case means that the internet is in trouble. So at first I thought that was on my end of me doing the experiment, but now that I took a look, actually the stream was set for exactly the same as last time. And so what that's actually meaning is that the number of people who are using the internet to broadcast video is increasing so much that it's actually not that our studio is glitching, but the internet is glitching, which is a bad sign. But maybe that's also a natural outcome because a lot of people are doing video conferencing, a lot of people are doing video calls, and maybe the internet's getting too much of a load. So then in that case, I have to say, hopefully we get faster internet in general. But let's keep going. I see it. Somebody already said multiply by 2 because this is usually what people do. So let's multiply by 2. Okay? So where's my pen? Yes. Multiply by 2. If you multiply everything by 2, the right-hand side is 2x. And the left-hand side is, it's nice. It's 1 plus 1/2 plus 1/4 plus 1/8 and so on. Now, why is it so exciting to multiply by 2? What do people usually do next? If you multiply by 2, what will you do with these two equations? Subtract, exactly. So you subtract, you take the second one minus the first one. Okay, so we go here, subtract. And if you subtract, 2x minus x is just the x. And over here, when I subtract, I just get, oh, this is wonderful. Look at all this canceling. This 1/2 gets subtracted from that 1/2. This 1/4 gets subtracted from that 1/4. And so on, right? So we're always going to subtract, subtract, subtract. All that stuff cancels out. What's left? Just 1. And so we're done. Okay? So that's good. So we got 1. So that seems reasonable. Actually, I'm going to go back to the place that I was before so I can see what you guys are also watching. Okay. I want to make sure I can see what you're watching because that also helps me to see the level of glitching that YouTube is performing right now. Okay, but we're back. Good, x equals 1. So this is great, this is all, we're done, right? But I'm going to show you something else that's kind of weird. All right, this seems reasonable, but now I'm going to show you something that should make you very, very concerned. What if I take 1 plus 2 plus 4 plus 8 and keep adding? Let's call that y. What should I multiply by both sides? Let's multiply 2 by both sides. Why not? You get 2. Y equals 2 plus 4 plus 8 plus 16 and so on. And now what I'm going to do is I'm going to subtract. Subtract. I get y, right? 2y minus y is y. What do you get if you subtract? Well, you can cancel a lot of things. This 2 will be subtracted from that 2, right? And it just keeps going. And if you just keep going, this 4 will be subtracted from that 4. And it keeps going. And we get something very, very interesting. We get that when you finish subtracting, all that's left is, this is 1 here, and you subtract the 1, so y equals -1. So I think I've just proved that 1 plus 2 plus 4 plus 8 and so on is -1. Do you agree with me? How many people agree with me? Somehow I think people don't like the idea of adding 1 plus 2 plus 4 plus 8 and getting -1. That makes no sense. Is the right thing to say. And what I want you to say is, wait a second, if I'm allowed to do it over here, why am I not allowed to do it over there? Can anyone tell me? What's the difference between the left and the right that make it okay on the left, but not okay on the right? Because math can't be like, sometimes it's okay, sometimes it's not okay. What broke on the right-hand side? I don't know anymore. Well, there's fractions. Indeed, there are fractions on the left. Maybe fractions make it better? Is that all? The right one diverges, says somebody who has probably taken some kind of calculus class. Somebody said, is it because of whole numbers and fractions? That's related to that. In some sense, because there are whole numbers, it's causing it to diverge, meaning it's causing the sum to be infinity. The real problem is that this left side is not a real number. when you keep adding and adding and adding, it doesn't get closer and closer to just one number. It gets bigger and bigger, and I cannot replace it with one number. The left-hand side, what's going on here, is that you're actually imagining that all of this already adds up to a number, and then all of this just adds up to twice the number. Strictly speaking, that's a notion in calculus called limits. So what I'll say is, if you know the stuff about calculus, you can then say this is good and that's not good. What if you don't know the stuff in calculus? I have another way to do it. Let's go back to the half plus a quarter plus an eighth, okay? Here's another way. We just add. What's 1/2 plus 1/4? Let's start with that. Half plus 1/4 is 3/4, okay? And we're just gonna keep adding, okay? Actually, I'm seeing all of these things. Somebody says calculus is scary. It is scary if you just memorize a lot of stuff. To be honest, it's actually not that hard if you can understand each of the things that you're using. Next, let's add 1/2 plus 1/4 plus 1/8. So that will be 3/4 plus 1/8, which is, how many eighths? 7/8. What if I do 1/2 plus 1/4 plus 1/8, you see where this is going, plus 1/16? That's going to be your 7/8 from before, plus 1/16, which is, I see it already. Do I see it already? Let's see. What do you have? It is 15/16. Who sees a pattern? If I add up these 1 over a power of 2, then if I look at the denominators, the last denominator is the denominator of the sum. So I'm circling those. The last denominator is the denominator of the sum. And what I'll say is that you can prove this with something called mathematical induction, but for most people, as you're looking at this one actually, you just see that it makes sense. I'll tell you another way to prove it if you're curious. Another way to prove it is just to think back about Zeno's paradox. In Zeno's paradox, what is this story? This 1/2 plus 1/4 plus 1/8 plus 1/16. This story in Zeno's paradox is exactly what's here. Zeno first walked halfway. Then he walked halfway of the remainder, and then halfway of the remainder, and halfway of the remainder. But instead, let's keep track of how much he had left to walk. After walking halfway, the distance that he had left to walk was 1/2. But then after walking half of that remaining distance, the distance that's remaining is half of the half. Did that make sense? This is why how much is left between that fraction and 1 is always cutting down by half each time. This is actually the easiest way to understand why this is. If you know more advanced algebra 2, you know this is the sum of a finite geometric series. But we don't even need that here. We just need Zeno and his rocks. So basically, one more step, the blue thing, gets him to half of the distance remaining. So if it was 1/4 remaining, the distance remaining after that blue is 1/2 of the 1/4, which is 1/8. And you just keep going. So if we go back to this sum of fractions, it is true that if I add all of these together, I'll always get a power of 2 and just one less than the power of 2. And there's the way to write it is actually the story I just said. This is 1 minus 1/16. So now once you write it that way, we don't even need to know calculus to conclude that Zeno's paradox says that Zeno will actually get there. Because if you go and add up all of these fractions, 1/2 plus 1/4 and so on, what happens when you finally get 1/2 plus all the way to 1 over some huge number like 1024? Well, I can say that's just 1 minus 1 over 1024. And what you should say is that every single step actually takes Zeno closer and closer. This part that you subtract, this part goes to 0. Is that clear to people? This actually explains exactly why the sum should go towards 1. If you go and add all these fractions, as you add and add and add, your distance between your sum and 1 converges to 0. Some people will then ask, hang on a second, is that the same thing as the sum being equal to 1? So now here's something which is also interesting. A lot of people also wonder, is 0.999999 repeating equal to 1 or not? Or does it just like get close to 1? And the answer to that is that whenever you write ... or whenever you think about Zeno's paradox, what you're thinking about is the dot 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 thing is just representing what number are you getting closer and closer to. And so the answer is, yes, the number you're getting closer and closer to until the distance approaches 0 is 1. And so Zeno's paradox is Zeno would actually, if you add up all of those things, would actually eventually get to the rocks. So that's I guess what I'll share about this Zeno's paradox. I chose this question because I thought I can also share a little bit about this mysterious letting y equals the sum of something and then multiplying by 2 and subtracting. I just wanted to show how this can be dangerous. On the other hand, if you are in a situation where the numbers already will add up to something that converges, that's what it's called, to an actual real number, then this part is okay. And that's actually what you usually see in school anyway. Okay, let's go and do some other question. We probably have time for one more question here. I see. So somebody asked about Monty Hall problem. So that's a problem about cars and goats and a game show with 3 doors. I'll say that particular problem is fairly sophisticated and probably too sophisticated for the audience that we have. Sorry, I don't want to say too sophisticated. I mean, it uses too many mathematical things that are taught after the grades that people are in right now. So I'd prefer to do some questions that might work for like the people who are in algebra or maybe some of the geometry. Hang on. Let's get this. Why does power of a point work? So I'm going to say, I'll give you a really quick answer to this, which is try playing with similar triangles. That'll get you a long way. Power of a point, use similar triangles. It'll get you a long way. Again, the reason I don't want to go too deep into that is that's actually a standard mathematics lesson that your teachers might already be teaching you. Or if you want like a different way, in fact, we also teach that already in our geometry course. Let me see, what else can I hit here? Our moderators have been picking out different things. What do we have here? I see the Po-Shen Loh technique on quadratics. That one I also want to say, hit the video that we already have. That will help me to be able to get more different people. I will say the reason I'm replying to some of these particular questions is because I want to at least give you a pointer if you ask that question. There's a 1-hour video that explains this Po-Shen Loh technique on the quadratics. What else have we have here? What else do we have here? I'm just looking at all of these things. What is 10 over 9997? I don't know. So I want to see. Okay, somebody said, what is 10 over 9997? Let's find out. And now you'll see how I think. 10. The way I think, I'll tell you one thing about the way I think. It's that I like to use white when I start writing the first thing. So let's go. 10 over 9997. What is this? Of course we could use a calculator, but I'm a little curious if we can approximate this, right? So what I'll say is this thing is, it looks to me like it's about 10 over 1 with 4 zeros, right? It's about 10 over 10,000. So I'll tell you your answer is going to be about 1 over 1,000. And so your answer will be about 0.001. Now, there's another part of me, though, which is always looking for a challenge. I'm kind of curious, if I have 10 over 9997, I want to know how far off am I? How far off am I with this 9997 versus using the 10,000? And I'll say that the way I often think about this is I think about how I would look at what we call multiplicative error. It's what I'd have to multiply this 0.001 by to get 10 over 9997. It's like this. If I had 10 over 10,000, if I multiplied that by 10,000 over 9997, well, that would actually be the thing you gave me. This product is actually the fraction that you asked me. So now my question is, what is that? About how big is 10,000 over 9997? Now I'm curious. So if I'm looking at this fraction, I'm going to rewrite that fraction. I'm going to rewrite that fraction as a mixed number. Can anyone help me? What is 10,000 over 9997 as a mixed number? So this should be 1 and somebody opening snacks in the background. That's true. I'll tell you the story in a moment, okay? So 10 over 9997 as a mixed number, yes, it is 1. I'll tell you the story at the end of this live stream. And please remind me to, because it's pretty interesting. 1 and 3 over 9997. And I want to write this as math, so I'll write a plus sign. Okay, by the way, I often think of this as the multiplicative error. I'm saying that my answer was 0.001, but I'm off by some factor. I think the thing I'm always curious about is, am I off by a factor of 2? Am I off by a factor of 50? Oftentimes in this real world, if somebody is looking at a number, what you care about is how far off you are by some factor. For example, if I told you that the distance between me and like New York City, if I said the distance between me and New York City is 1 mile, that's way off. That's off by some huge factor. But if I tell you the distance between me and New York City is something like around 500 miles, that's suddenly a lot better. I'm definitely not off by more than a factor of 2. So sometimes people even call this percent error. It's like I'm only off by 1% or 2%. That's great. And this is telling me what percent error I'm off by. What is 3 over 9997, approximately? Well, this 3 over 9997, I can actually say that the 3 over 9997 is approximately 3 over 10,000. You might say, it looks like I've just used this again, right? I'm making another mistake on the 9997, replacing it by 10,000. We'll get to that, okay? So it's 3 over 10,000. And if it's 3 over 10,000, what's that as a decimal? That is 0.000, how many O's? Is it like this? The reason I'm pausing is because I'm actually not used to writing this many O's. So that's a lot of O's we have here. 0.0003. Okay, so in that case, what this is telling me is that I'm off by 0.03%. I'm not off by 3%, I'm off by about 0.03%. Because if I add these together, 1 plus 3 over this number, this sum, this whole sum here, is going to be about 1.0003. So this is telling me that my answer is going to be like 0.001, but that's off by a factor of about this. What that means is 0.001 is actually pretty close. So I will say that the answer of 10 over 9997, about 0.001, I might be off by a fraction of a percent. You might have heard of that way of speaking before. This is what we call a fraction of a percent off, like 0.03% off. And that's pretty satisfying. And now you might wonder, did I make a mistake here too? Well, yes, I did. And the mistake I made there is it's not really off by just 0.03%. That 0.03 itself is slightly off by another, it'll be another 0.03%. So actually it's like 0.0003 and then some more O's and then some other number there, probably like a 9 and so on. So I'll say that that's my answer to this question. In fact, it's even making me hypothesize that the answer to your question is going to be something like with 0.001s and then like 3s and then 9s and then 27s and then 81s. I'm actually a little curious. Did anyone punch this into their calculator? Did this thing turn out after you punch it into your calculator to have like 1, 3, 9, 81? I'm a little 1, 3, 9, 27, 81. I'm a little curious. It may or may not because I'm just doing that part in my head. But if anyone has a calculator, if you could use your calculator or Wolfram Alpha to like multiply this out and paste it in there, oh my gosh, it does that. It's 139, and the next thing you'd see is 2781 and so on. If you want to know why, the reason is it's related to the sum of a geometric series. It's very related to this 1 plus 1 half, this half plus 1 quarter plus 1/8 plus 1/16 and so on. But I'll tell you how I thought of it. The reason I thought of it is because I saw myself repeating this switch from 3 over 99, from something over 9997 to over 10,000, and seeing that I'll have to repeat the switch and repeat the switch and repeat the switch. And so that was indicating to me that we would probably see this 139 2781 pattern. Okay, I did promise you the snack story. Okay, so actually what I'll say is you may often hear background noises in this studio. Sometimes it's because it's from the people who are helping to run the live stream. The live stream takes a team. Sometimes it's also from other people who are also working on important things. Something you may hear about soon, maybe next week, is that I actually came up with an idea that possibly could help to reverse the coronavirus, or to help save a lot of lives. I got this idea on Sunday night. It uses math, actually. I was just thinking about the whole thing as a mathematician. And as soon as I got the idea on Sunday night, I said, oh, we got to try to do this. And so, in fact, a team of amazing people came together, and we're now all working on this together. Exactly what we're doing, it's still secret. However, as I said, we hopefully will have something to show not just you, but the entire world at the same time at some point next week. And let that just maybe be a message to you. In fact, I'll also tell you that's why when we were running this live stream, I have a lot of other things that I also generally work on during the day. And so I was in fact switching gears between working on trying to stop coronavirus and then switching into let's try to help everyone understand some mathematics. Somebody asked about applied mathematics. Yes, actually it does have a lot to do with applied mathematics. I didn't come up with social distancing, if that's what you're wondering. But I will say that that is something that is useful, right? But I decided to end with this story also to show that people who do math don't only just do a bunch of calculations like this. People who do math don't only wait for someone to ask them a question that they're curious about, like 10 over 9997, which made me want to know the answer, right? People who do math also can use whatever they understand about math to go look at real problems in the world. And when the real problem in the world is big enough, sometimes you say, maybe we should just think harder. And with that, I encourage all of you, if you find this kind of math problem interesting, if you like to challenge yourself, keep learning, and maybe someday you might come up with some idea that's also useful. We'll see. The big world problems need more than one person to solve, and as I mentioned, that takes a team. So that's why we occasionally have background noises. But regardless, we will still always talk about math, and if you liked what you saw today, please do tell other people. I do see that we have over 200 people here. And what we will always do is we'll try to find a way that reaches mathematics that can be understandable to as many people as possible, while at the same time hopefully giving a new view into something that you may not have thought about before. See you next time.